All right, chemists, so let's get started. Hopefully you've looked at the board here to see your responses to that last recitation 12, where I asked you what words come to mind when you think of chemistry. So these are your responses in a word cloud. So the larger they are, the more times that word came up within within the responses of your classmates. So I think it's funny. I do this every year. It's the same words kind of come up here. I'm glad that I see, elements, experiment, molecules, reaction, structure, though I don't see composition in here. But I see the same things every year. And I'm not surprised that I see other, less, the funny words here, like stressful, cry. I see some barnyard noises. Last class, I gave a different one. I have a different one for the 410 class. Someone put chicken, and I like that. And made it up on here. But you guys have some barnyard noises on here. Exhaustion, and that's all right. You guys have worked so hard in the past, 15 weeks. We just have a couple more days here, so hopefully you can just listen to me rant about diamonds for chapter 12. It'll just be an enjoyable time. Yeah, and so as promised, also here are the results for our favorite chemistry word. So I think the winner is electron. All right, between electron and enthalpy, electron 1. I asked this question again in 1220. Who's taking 1220 with me? Okay, good number of people. Sorry, you also have to wake up at 8 a.m. I also have to be up at 8 a.m., so that's unfortunate for me. I asked this question again, but it's between enthalpy and entropy. So you have a couple months to think about what you want to say. All right, and also I asked, would you prefer a all conceptual based exam or math calculation based exam? So 2/3 of you said a conceptual exam, which I'm surprised because I have planned here after we finish chapter 12, it's a really short chapter, I'll have us go over some of the most missed midterm 1, 2, and 3 questions and some of the statistics for that. And most of the questions that were did the most poorly were actually conceptual based questions. Okay, yeah, some of you aren't surprised. Yeah, so those are the harder ones. So maybe you'll regret what you said here. Okay, all right. Also some announcements. Do look at that announcement I made on Friday about final grades going in. I need to finalize the grade book on Sunday, December 11th. Basically, I need to put a bow on all of the grades minus the final. So basically your final exam grades will come in, we'll plop it into the spreadsheet, and then it'll go off for calculation for your final letter grade. So that means we need to finalize recitation grades, homework grades, your lab grades will be finalized. All of those need to be set in stone before Sunday. So I need you to check your recitation grades right now. Basically, the grade that you see in recitation, in that grading category, is the grade that's going to go to the grade book unless you talk to me. I already have incorporated the 2 drops. So, you only need to go to 10 of 12 to get 100%. So do recognize that. If there's a discrepancy, talk to me, email me as soon as possible, because this happens every year. Students, after the final exam, they're just trying to scramble to get more points. No, this all has to be done prior to the final exam. No, point grabby at the end of the semester. Also, again, I need to finalize the grade book on Sunday. So that means online homework. The last day to submit anything will be on Sunday, this Sunday at midnight. That includes any late assignments. Remember the really lenient policy, you can get 50% of any remaining questions you have. Never ever, request an answer, just, answer it late. You'll get some points. The last day to submit those is on Sunday at midnight. Also, chapters 11 and 12 will be due on Sunday at midnight, meaning that there won't be any grace period, all right? So that's the last day to submit them. Basically what I'm gonna do on Sunday or Monday morning, I'll wake up, I will sync the grade book manually one last time and then desync it entirely, meaning that you will still have access to Mastering Chemistry. You can do problems or whatever, but any points you earn after Sunday will not go to the grade book. All right, so like this can't happen. After the final exam, you feel like you didn't do well and you try to do more online homework to boost your grade, it's not gonna happen. So that hard deadline, it's a hard deadline. Yes, question? You will get your exam grade from the final when your letter grade goes in. Yeah. Well, one, you're not, we don't give back the final exams, like we keep them hidden. We've given you the midterm exams, but we keep the final exam hidden. And basically, your final grade is what determines your letter grade. So we release them at the same time because there's no curve unless something crazy happens. Like everyone got 100%, all right? Like then we would not use the grade scale, we would adjust it. But like from what I've heard, the grade scale that we have posted in the syllabus, that's what we're going with. So your final exam grade will determine what your letter grade is, yeah. Probably the very last day grades will go in. There are 2,000 of you, and we have to wait for every single student, every single every single 1210 student to take this exam. The last makeup day, I think, is Friday. I think the makeup day is Friday, and we can't do everything. We can't put grades in until all Gen Chem students take the final. Okay, all right, yes, cool. All right, and do double, triple check when the final exam is according to our syllabus. It's on Monday at 8 p.m. in this room. That's really important because if you miss that, all right, we were really lenient with midterms, all right? If you missed it, we just gave you a makeup at the end of the year. But for the final, if you miss the final and you have to take a makeup, there is a 15% penalty. Yeah, so do not miss it. Do not miss it because we need to get all the grades in so we can release grades. All right, okay. All right, there we go. All right. All right, so where do we leave off? Okay, chapter 11, we're just about done here. Remember on last week, I boiled water at room temperature. I was able to do that by reducing the pressure, the external pressure on that room temperature water. Because there's two criteria we need to think about whenever we want to boil water. First, we need to supply enough kinetic energy through temperature to overcome IMFs, but we also need to overcome any external pressure. Usually that's the atmosphere when we're just boiling water on Earth, but I had my big boy vacuum pump and I was able to reduce the external pressure on that water in that bell jar. So I was able to reduce that pressure, making it easier for water to boil. And so that's because I reduced the pressure inside that bell jar to be equal to the vapor pressure of water at that temperature. And so vapor pressure is essentially the gas particle of that liquid. Those particles, some of them have enough kinetic energy to escape the liquid phase, and oftentimes we think of these liquids as volatile because we can smell them. The trends that we see with vapor pressure is typically as your tractions between particles increases, your vapor pressure decreases because the particles are holding particles in the liquid phase more tightly, but also temperature increases, vapor pressure increases as well. And so we looked at some common, substances, water and acetone. We know acetone has a very distinctive smell, meaning that it exerts a high vapor pressure at room temperature, meaning that water, because it has a low vapor pressure at room temperature, has stronger IMFs. Their particles are more attracted. And we see also that, vinegar heated up is going to smell more strong, again, because temperature will increase your vapor pressure of your sample. And so the big idea here is that any substance will boil when the vapor pressure of your sample is equal to the external pressure. So you can either boil a sample by increasing its vapor pressure by increasing its temperature up until its boiling point, or by reducing the external pressure, right? And so this is where, I was able to boil water at room temperature because on Earth, water will boil at 100 degrees Celsius because the external pressure is 1 atm. But in the bell jar, I was able to reduce the pressure to something lower, meaning water would boil at a lower temperature, something lower than 100 degrees. And so this is the same reason why water, there's oftentimes like different baking instructions for, boxed brownie mix or something like that for high altitudes. So to kind of put this in an analogy or an example, Denver, we've already talked about Denver. It's higher up, it's the Mile High City. There's less external pressure because there's less particles on, people's heads there. So the atmospheric pressure in Denver is 633 torr, or about 0.83 ATM. So it's only like 80% of 1 ATM, like what it is at sea level right here. Water will boil at 100 degrees Celsius at sea level, at 760 torr. But in Denver, will water boil, is it harder to boil water or easier to boil water? Easier, yeah. So that means when you boil water, it's not going to stop and start boiling. The temperature isn't going to stop at 100 degrees. No, it's going to stop slightly lower. We'll just say like 95 degrees, all right? That water will boil only at 95 degrees in Denver, meaning that when you cook things, you're cooking at a lower temperature. So oftentimes on like these brownie mixes, it'll say, hey, cook the instructions, like take that time and cook it a little bit longer because you're cooking at a lower temperature when you're in Denver, because we're operating at a lower external pressure. Versus, does anyone know what this is? Yes, that is a pressure cooker. So that's like the more manual looking kind, but I think it's a little bit more obvious. So kind of on the flip side of that, if we boil water, the external pressure is lower, the boiling point temperature is lower, all right, lower than 100 degrees. But in a pressure cooker, we're literally boiling water in an enclosed container where we have a weight on top of the opening. So this weight, we're putting additional weight on the water. So in order for water to boil, it has to get through external pressure and this little weight on top of the cooker. So this is how we can get water to boil at a higher temperature than 100 degrees Celsius. So oftentimes if you look at recipes for a pressure cooker or your Instapot, it's the same thing. It's just fancier and electronic. An Instapot's the same thing. You're cooking at a higher temperature than what limits you. Water typically only boils at 100 degrees, but in a pressure cooker, it's actually higher. So you'll often see recipes that are shorter time, shorter cook time when using a pressure cooker, because the boiling point of water is higher. And it's due, I got one of these as a wedding gift from my in-laws. I haven't used it yet, unfortunately, to like do canning and stuff for like my garden, which dies every year. But yeah, that weight, you're essentially forcing water to get through more weight. You have to heat it up higher in order to increase its vapor pressure above that additional weight. Yeah. I don't know. You can probably look it up on the document that I provided. I mean, how many are there you need to know? 1 ATM equals 760 torr, millimeters of mercury, equals 14.7 psi, and then like 101.325 Pascal. I think that's it. Yeah, I would look it up. I'm not sure if it's given, but yeah, the 760 ones you should definitely know though. Okay. Yeah. All right, so that's boiling water. All right, so let's look at some vapor pressure curves. So we looked at water. All right, water will boil when it's at a temperature where its vapor pressure equals 1 atmosphere, 760 torr. So let's look at water and ether. Here I asked, we're comparing diethyl ether and water. So I'm asking here, which substance is more volatile at room temperature? Meaning, which one exerts the higher vapor pressure at room temperature? So to read this graph, we see vapor pressure on one side, temperature on the other side. So if we look at room temperature, let's say it's about 20 degrees is room temperature. Based upon these lines, blue lines, water, diethyl ether is the red line, which one is more volatile at room temperature? Ether, yeah, ether is more volatile. It's exerting a higher vapor pressure. It's going to be the more smelly one. All right. Okay. So based upon that, the comparison, the difference of vapor pressure, room temperature, which substance contains more IMFs in its sample, ether or water? Water, yeah, because the particles are hugging tighter. They're hugging each other tighter because it's exerting less of a vapor pressure at room temperature. And then finally, from the graph, which one has the higher normal boiling point temperature, water or ether? Also water. You can read it off the graph because remember, any substance will boil when its vapor pressure is 1 atm. So ether actually boils at 35 degrees Celsius while water boils at 100 degrees Celsius. So you can see it from that graph. But you could also take it from trends too, because we know water has more IMFs. It has the higher boiling point temperature as well. But the graph tells us the exact same thing. All right, so we learned that we can make something boil or change phase by changing its temperature. We can also learn, we learned here that we can make a substance boil by changing the external pressure on it. There's different ways we can change phase. Changing temperature or changing pressure. So we can put both temperature and pressure in the same diagram. That we call these phase diagrams. So basically these phase diagrams tell you what physical state a substance will adopt at certain pressures, all right, if we increase pressure on the y-axis or increase temperature on the x-axis. When we think about normal boiling point, normal melting point, these phase changes are happening at a constant pressure. So to figure out, okay, what's the melting point, what's the boiling point of a substance, we will oftentimes look at one pressure, go across horizontally to see at what temperature do those phase changes happen. So know the different solid, liquid, gas regions of a phase diagram and the different phase change names that we discussed before. We can melt a substance, by increasing the pressure, increasing the temperature. We know, like, to melt something, that's what you do. But according to this diagram, we could also go take a solid, reduce its pressure, and see how we cross the solid liquid line. We can also change the phase from a solid to a liquid by changing pressure as well. That's what this phase diagram says. All right, so do know the different regions, the different phase changes, and we'll talk about these fun points here, the triple point and the critical point in the next slide. So here is a phase diagram for CO2, all right? So CO2, do you all know what dry ice is? We think about like ice, water ice, right? Water's wet, but dry ice is dry. That's weird. All right, so we call dry ice because we think about that block of dry ice as a solid. Does it ever become a liquid? No, it goes straight to a gas. That's why we call it dry ice. So let's see, can you locate where the melting point is of the normal melting point of CO2 on this phase diagram? So remember, what does normal mean? At 1 atm. So we're looking at 1 atm, all right, on this diagram, and it's right here. What is this phase change right there? Is that melting? No, it's not melting. It's going from solid to gas straight. So that is sublimation. Yeah, so this is why we call dry ice dry ice. On Earth, at 1 atm, there is no solid to liquid phase change. That would happen maybe if we were, on some other crazy planet where it was 100 atm. All right, if it was 100 atm and we increased the temperature, yeah, we could make solid CO2 melt to liquid CO2, but that's not the case here on Earth. So that is why we call dry ice, because there's no melting phase change there. Okay, so triple point and critical point temperature. So what are these? The triple point, which is in the center kind of this graph where the solid, liquid, gas lines all come together. So at this specific temperature and pressure, your solid, liquid, and gas phases are all at equilibrium. What that means is that they all exist at the same time at that specific temperature and pressure. I once accidentally made the triple point of cyclohexane by accident. What it looks like, because you might be wondering, what does a triple point look like? It looks like something that is boiling and freezing at the same time. It'll like boil, and then it'll freeze, and then it'll boil, and then it'll freeze. And it just keeps doing that, and it was pretty cool doing that. So that only happens at a specific temperature and pressure, all right, where all three of those phases exist at the same time. So that's the triple point. What's kind of more interesting and more useful to us is actually the critical point. So thinking about, you know, changing phase. We can boil water, turn it to a liquid to a gas by heating it up. We can also change phase by changing pressure. We actually do this if you've ever filled up a propane tank. If you've ever filled up a propane tank, propane is what? What phase? When you put it in your grill, it's a gas, right? It combusts, it's a gas. But when you store it in these Blue Buffalo, you know, those propane tanks, if you slosh it around, it's actually a liquid. All right, we store it as a liquid, but once we open up the canister, it's a gas. Because in these containers, it's under high pressure. It's not super high, but high enough inside the container to have high enough pressure to liquefy that propane from a gas to a liquid. Because it's easier to store liquids than it is a gas. We are utilizing our phase diagram here of propane. So if we just pretended like this graph was propane, essentially you could think, oh, okay, like here is the gas phase when you're like lighting your grill, but when it's being stored in the tank, you can think, oh, you just increase the pressure so it becomes a liquid. So what the critical temperature is a certain temperature where this can no longer happen. If the temperature is too high, all right, if the temperature is too high, there's too much kinetic energy. You can't push and pressurize your sample enough to make it liquefy. So this is what we call supercritical fluid, that basically these fluids can withstand, or essentially they're gases, but they have a lot of fluid nature characteristics to them. There's so much kinetic energy that you can put these substances under tons of pressure and they won't liquefy. And this happens at a certain temperature. So we call that a critical point temperature. So for example, water, its critical point is rather high, that essentially under a lot of different temperatures, you can still re-liquefy water vapor. But once you're above, what is this? 375 degrees, then you can no longer do that. With what we see here with CO2, the supercritical point, the critical point for CO2 is at a much lower temperature. It's only about 31 degrees Celsius. That at that temperature, there's too much kinetic energy to liquefy CO2, even if you put it under really, really high pressure. So this is what we call supercritical CO2. It's fairly easy to make. Supercritical CO2 has gaseous and liquid properties to it, and it's actually used in a lot of different industrial applications. They use it for extraction, green chemistry, because you're not polluting water. You're just using CO2 instead, and it'll separate and just go into the atmosphere, so it's used for green chemistry. There's a lot of different applications for supercritical fluids. And the general trend that we see here is that the stronger the IMFs in that sample, the higher the critical point temperature that it can withstand. It is able to be compressed into a liquid for higher temperatures. Just something like water, because it has high IMFs. CO2 has rather low IMFs, so we see a lower critical point temperature. All right, and so like with propane is all non-polar, it's fairly light, it's a gas, also has a fairly low critical point temperature. So if you get this propane tank too hot, you may not be able to re-liquefy it. So if you were trying to fill up this propane tank on like the sun, maybe, then it won't work. It won't work. All right, according to our phase diagram. All right, so that's chapter 11. So chapter 11 homework is due on Sunday. Everything is due on Sunday. Okay. So we'll move on to chapter 12 now, all right? But keep the ideas of intermolecular forces in your back pocket. It's all important. It's all important. All right, chapter 12, gases. Or sorry, solids. Yes, we talked about gases. Chapter 11, we talked about liquids and IMFs, taking your gases, making them hug each other, attracted towards one another. Now, chapter 12, we talk about solids. So IMFs are still a important point in chapter 12, but there's in some instances, some types of solids, we think about IMFs. Sometimes we think about other types of bonding. So there's lots of different applications of earlier chapters, and I try to incorporate some review. In this chapter, oftentimes we're going to bring back the concepts of IMFs, but we're also going to talk about the different types of bonding, ionic, covalent, that we've talked about in previous chapters. I think these slides only have like 28 slides in it. I've basically taken out everything from this chapter except the learning objectives for the exam, and a couple slides where I just rant about diamonds. So hopefully I can get to that today. Okay, yay, yeah. All right, so solids. There's two types of solids, crystalline and amorphous. We care about crystalline solids because we can predict trends, structures when it's crystalline. All right, so we're going to focus on those. But amorphous solids have their place too. Amorphous solids, there's less order in where the atoms are. That's not really fun to study if there's no order. So we're not going to be really looking at those. But you can think of amorphous solids as frozen liquids, essentially like your liquid is at one point flowing and then it just stops where it is. So they don't crystallize into an efficient packing like we'll see in crystalline solids, so we don't really talk about amorphous solids. We don't talk about them. Okay, so we'll look at crystalline solids. Fair? Okay, so of our crystalline solids, there's 4 types. I hope I've prepared you well for this point, where when we look at chemical properties, we need to consider composition and structure. So the composition of your substance will dictate whether it is going to adopt a metallic bonding solid structure, ionic bonding, network covalent, or molecular. So there's certain criteria you want to look for in the formula to help you determine, okay, what kind of bonding is happening. There's 4 different types. Metallic bonding. You want to look for metals. Metals have metallic bonding. Ionic bonding. What's involved in ionic bonding or an ionic solid? Ionic substances. So you want to look for ions. What are typically ions? How do you form ionic compounds? You need a metal and a non-metal. So that's chapter 2 stuff you got to take out of the deep depths. But it's all coming back. And then finally, the last 2 are a little bit more difficult to distinguish. Because they're both made of nonmetals. So we have network covalent solids, and then we have molecular solids. You'll see here both of them are made completely of nonmetals, but their bonding is different. Network covalent solids, all of the covalent bonds are bonded to all of the other atoms in an extended network that goes on forever. Versus molecular solids, we have covalent bonds combining a molecule, forming a molecule, where then the molecules are attracted to one another via IMFs. What's stronger, a covalent bond or an IMF? A covalent bond is much, much, much stronger. IMFs are really, really weak, but they decide a lot of properties that we see. So covalent, the substance with all covalent bonds, network covalent solids, are going to have really high melting points because their bonds are so strong. Right? And it's a whole network, right? You'd have to break all of them in order to get it to melt. Versus molecular solids, when you melt a molecular solid, you're just breaking some of the IMFs. So they have low melting points. So it's the bonding that dictates a lot of the properties that we see. All right? Okay, there we go. Good. Okay. These 2 are the hard ones. Okay. So some of the properties, and it all has to do with their bonding. Covalent network solids, really high melting points, really hard substances. Their solids are insulators, if they're made of nonmetals. All right, or semiconductors if they're made of metalloids. Metalloids. Okay. Molecular solids, on the other hand, they're very soft because, again, it's IMFs that are holding them together. We're looking for discrete molecules. When we melt the substance, we're just breaking IMFs. Also, covalent network solids typically are not soluble in water, because their bonds are so strong. But again, I want to compare this to molecular solids. Since the IMFs are so weak, they sometimes are soluble in water. But the distinction here is that they're not typically those solutions. When you dissolve molecular solids in water, they typically do not conduct electricity in an aqueous solution unless it's a strong acid, unless it's an acid or a base. So that's a small detail there. All right. And then these molecular solids have low melting and boiling points, again, because of the presence of IMFs keeping those molecules together. So that's the distinction of those two. They're oftentimes confused because they both contain all nonmetals. It's just the structure is different. Okay, let's talk about metallic solids and ionic solids. Metallic solids, they do conduct electricity. They're strong but not brittle. You can read all of that. Ionic solids, yes, ions are present. Okay, so this is weird. Like NaCl solid does not conduct electricity. If you took a piece of rock salt and you took some probes and like measured its conductivity, it would be 0 because conductivity is looking for free ions moving. When we have NaCl in the solid phase, are those ions moving? No, they're fixed there. But as soon as you dissolve NaCl, once you dissolve NaCl, you add water, now those ions are free. And those solutions do conduct electricity. So ionic stuff that's in solution, aqueous conduct electricity, but the solid forms do not. But if you turn NaCl molten, so make it a liquid, if you melt NaCl solid, because in the liquid form, those ions do flow past one another. Those do conduct electricity, but you're not very likely to run across molten NaCl on the street. So, but you're much more likely to run into NaCl aqueous. But both of them are conductors. Okay, those are ionic solids. They typically have high melting and boiling points too. They're hard, but oftentimes brittle, except some of our gemstones. Not all of them are brittle, but they can be. So those are the properties. Has a lot to do with the bonding, the nature of the bonding, and we determine that from the composition that they have. So we're bringing everything together now. So let's do some questions. Okay. Based upon these descriptions, what are these? A solid that's soft at room temperature, very soluble in water, and whose aqueous solution does not conduct electricity is most likely to be what? What do we think? Molecular? Molecular? Does anyone disagree? Okay, yeah, I think it's molecular too. What gave it away? What is it? The aqueous solution does not conduct electricity. Yeah, okay. I thought soft. Soft too. Yeah. Okay. Next one. A solid that is shiny and malleable, completely insoluble in water, but whose solid conducts electricity is most likely to be what? A metal. Yes. Very good. Very good. Okay. All right, last one. At room temperature, NABR is expected to be what? A gas, a liquid, a conducting solid, a brittle solid, or a soft solid. So this is where we have to take the idea, what is it composed of? What's its composition? And then what class of solids does that fall under? What is NABR? Ionic. So think about the ionic properties. Ionic solids typically have really high melting and boiling points, so it's most likely to be what phase? A solid. So we can eliminate A and B, a gas and liquid. So now what kind of solid? Conducting, brittle, or soft? Brittle, yes. Because conducting would be what? That would be a metal, right? Soft would be molecular, and then brittle would be ionic. Yeah. Gas and liquid would be what? What kind of What kind of substance? It would be molecular as well. Because if their boiling and melting points are so low at room temperature, they could be gases or liquids. All right, so there we go. Good? All right, so taking composition, understanding what category and what properties you would see for those different categories. Okay, DAD, yes, there we go. All right, so I mentioned that solids have order. All right, the crystalline solids have order. So we need to come up with a system to tell scientists where we can find atoms in the solid structure. We call these crystal structures. So in order for scientists to communicate crystal structures, you need to understand basically the basic unit of these crystalline structures, and that's the unit cell. We have this basic repeating unit in a extended solid, right? We have a solid, a ton of repeating atoms. We need to find the simplest unit that's repeating, like a wallpaper. So what scientists use are what we call unit cells, the smallest repeating pattern. So depending on how the atoms are arranged, these are what we call the two-dimensional lattices, because it's easier to think in 2D before you have to start thinking in 3 dimensions. So let's think about 2 dimensions first. So each of these black dots are an atom, right? So in this picture, the square lattice, we have an atom in each square. All right, each of these atoms are, 90-degree angles from one another. They're all equidistant. So the unit cell is just this repeating square pattern. That's why we call this a square lattice, where each dot is that atom in the center. But what if we offset the atoms where they weren't all 90 degrees? We could change the unit cell to be, what is this? What shape is that? I called it a rhombus last class, and then someone nicely corrected me. It's a parallelogram. Is that what it is? Yeah, because the sides aren't equal. Yeah, I don't know. Yeah, so we have a different shape here. The new repeating wallpaper unit is no longer a square. It's this parallelogram to give us the repeating atom and the angles that are created there. We can also have rectangular lattices and hexagonal lattices, and again, all dependent on how the atoms are arranged in 2 dimensions. Okay, these are tiles. You do not have to memorize these. I just want you to know that they exist, that atoms can exist in different ways in space, and that we need to come up with a unit cell. All right, but do solids exist in 2 dimensions? No, they don't. They exist in 3 dimensions. So taking from the base set of the 2-dimensional unit cells, we can come up with our 3-dimensional unit cells, and that's what that we have here. The simplest is the cubic unit cell. Not that many substances adopt cubic unit cells. You need a lot of order, a lot of symmetry in order to get a cubic unit cell. But this is our 3 dimensions. And again, so now we have more angles to worry about and more side lengths. And again, you do not need to memorize these. I just want you to know that these exist. If you look up a solid, if you just look up like titanium dioxide on Wikipedia, all right, you'll see titanium dioxide, its IUPAC name, its molar mass, and right under it, you will see its crystal packing structure. I promise, if you Google it, it'll say something like hexagonal blah, 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 all right? And I want you to know what that means, okay? That it just means, oh, that's how the atoms are packing. In 3 dimensions, that is its unit cell. So please tell us, what is titanium dioxide's thing? It should be in the box that's in the right corner. Or do you have it? You don't have it? Wikipedia didn't come up? No, okay. What is it? Okay, where is it? Atomic number, space group, look for space group. Where's space group? Oh, you just have titanium, but that's okay. Crystal structure, hexagonal close pack, that's what it says. Very good. Hexagonal close pack. All right, and so all of these basically it's the different building block, okay? But you can think of these as bricks. So any solid that you look up will have what is called a space group associated with it. You don't need to memorize these. I just want you to know their purpose. If you do a lot of solid state material science, then you will learn about these different structures, I promise you. Okay, so All right, metallic solids, let's actually put atoms in our unit cells. How can atoms pack differently in 3 dimensions? So I mentioned the unit cells, the simplest unit cell, 3 dimensions, is cubic. So we're going to talk about cubic for the rest of this class, putting atoms in a box, in a, equilateral box, because that's easiest to think about. So basically, these next slides are thinking about, okay, how can you put balls most effectively in a box? There's a lot of different ways to do it, actually. So if we have a cubic lattice, there's different places we could put our atom. If we had the repeating unit of a cube, we could put an atom on each corner. All right, and then repeat that 1,000,000 times. All right, so we call this a primitive cubic lattice. There's actually nothing that really adopts this structure because it's the least efficient packing. Because if we have an atom on each corner, only 1/8 of the atom is inside the unit cell. So if you counted how many total atoms are actually inside that cube, how many atoms are inside it? Is it 8? It's only 1, yeah, because there's only 1/8 of it and there's 8 corners. So we can make it a little bit more complex and fill more in the space. So this would be like if you had balls, all right, and you had like ping pong balls and you wanted to put them in a box, and you made like a square of like 3 by 3, 9 ping pong balls, all right, and then you put the next 9 directly on top of it. And then you put the next 9 directly on top of it. That's very inefficient packing. Okay, so then the next idea here is, okay, well, what if we have that primitive lattice, so an atom on each corner, but also an atom on the inside? Now we're increasing efficiency, packing efficiency, if we can put atoms between the vacancies of other atoms. And that's what we see here. So in a body-centered cubic lattice, body-centered meaning that there's an atom in the center, we actually have 2 atoms total in this packing arrangement. So it's more efficient than our primitive. And then finally, the more efficient packing is face-centered cubic. So if we look here, we have an atom on every corner, all right, again, but now we also have an atom on every face of our cube. How many faces are on a cube? 6, yeah, so there's 6 atom halves being added here. So this is called face-centered cubic. We still have an atom on every corner, but now we have an additional 6 on each face. This has the most efficient packing. I think there's a total of 4 atoms in that box. That's the best packing efficiency. All right. See, and so you would want to adopt some type of pattern like this to get all those, as many ping pong balls into that box. So if your job was to, do a cost analysis of shipping ping pong box as a distributor, then this type of thing would come in handy, right? All right, so another way to think about packing solids, if we think about this layering technique, all right, we already know it's really inefficient to put like one layer of atoms directly on top of another layer of atoms, because those 2 spheres, when they're like this, it's very inefficient in terms of packing. So how we can think about efficiency and making best use of our space is what we call close packing. This is the most efficient way to pack and layer things to take advantage of vertical space. But there's some details here. There's actually different ways you can close pack, where we kind of offset the atoms from one another, right? So if we have a layer, our first layer of, let's say, ping pong balls, do I want to put an atom directly on top of my second layer? No, I don't want to put it there. That's going to be inefficient. I want to put it in a void. But I have 2 options. There's actually 2 different voids, divots, that I can put that next layer. I could pick the yellow layer, or like the yellow spot, or the red spot. So step 2, if we put the second layer in, so what the book shows you is they put the second layer on top of the yellow positions, all of here. So what you see coming through are these red positions. I didn't put an atom there. I put them on the yellow positions. So there's our second layer. So what I'm trying to get at with close packing, there's actually two different patterning options here. We can have an A-B type pattern of layering or an ABC type layering, and they're unique. So I like to show the side view. So the ABA type layering is, this is layer 1, that's layer 2. Your third layer is going to be directly on top of your original layer. That's why it's called ABA. And this is called hexagonal close packing. This is what titanium adopts from that Wikipedia article. Yay. Okay. So the other way we can close pack, we still start with layer 1 and then layer 2. So we have A, then B, but if we look at the third layer, C, we actually, that third layer is not directly above the original A layer. It's actually taking the other vacancy that we didn't take before. So this red layer. So this is ABC type layering. And so we call this cubic close packing. Right? It has the ABC type layering. Both of these arrangements have the exact same packing efficiencies. So I don't know the details of why one is preferred over the other. You might need to talk to solid state chemist expert who is on one of the book authors of our textbook, and we'll talk about him, and I'll clown him at the end here of the chapter. Because he wrote the book. He can put anything in the book. So like he put all his stuff in the book. All right. So there's how we can pack atoms. Metallic close packing. I think the important thing here is to associate AB type patterning, your layers, with hexagonal close pack, and ABC with cubic close packing. Okay. All right. So types of solids. Metal solids. All right. So all of these contain metals. There's different ways we can play with metals. So the first way is elemental, pure elements, metals. All right, so like pure gold, pure silver, pure copper, all those things, where all the atoms are identical in your crystal structure, in your unit cells. All right, that's boring. Those are all our elemental things, because believe it or not, when we interact with metals in real life, rarely are they elemental. When we think about pure gold, pure silver, pure iron, they typically don't have the right kind of properties that we want to do what we want. Gold, it's shiny, all right, but it's really soft. So we'll add other things to it to hopefully keep the properties we want, the shininess, but also increase properties that we want to add, or we do want, like toughness or durability. So oftentimes when we are thinking about metals that we interact with on an everyday basis, we're typically talking about alloys, a mixture of metals. So these are homogeneous mixtures. They just happen to be in the solid phase, where we have different elements present. So there's actually two types of alloys, substitutional and interstitial. Actually, I want to talk about both of these real quick, alloys and intermetallic compounds. Both of them are technically mixtures here. The difference between alloys and intermetallic compounds is that alloys, the composition is typically given as a percent because it's a mixture, but intermetallic compounds are typically given with a formula because the ratio of atoms is more set based upon a pattern. So yeah, alloys, typically a percentage. So of the alloys, the ones that it's just like, 50-50 mix of like gold and silver or something. Two types, substitutional. Substitutional is where you have a crystal structure of like your main element, so this case gold, and you literally replace some of those gold atoms with another metal. This typically happens, substitutional happens when the atoms are similar sizes. You can just swap them out like no one noticed, okay? So some examples of substitutional, 14 karat gold, where you, replace not nearly 50, not 50%, but nearly 50% of the gold atoms with silver atoms instead. And probably some other things as well, but a little bit more than 50% of the atoms are still gold, but you're just swapping out those gold sites. Other substitutional alloys, bronze and brass, just different combination of elements. Mostly, bronze is mostly copper with some tins, substituted brass is copper with some zinc. substituted in it, all right? Because copper, pure copper, like degrades really easy. Remember where it is on the activity series? All right, so mixing it with other things will help its durability. All right, so that's substitutional, just swapping atoms. Interstitial happens when the atoms, the element that you want to add to the mixture, there's a big size difference. Because what we're looking here is steel, mixture between carbon and iron. So carbon is a lot smaller than iron. So doing a one-for-one swap for sites isn't very good. So instead, carbon is just going to live in the vacancies of the main iron lattice. So you see here, iron, your crystal structure, that repeating unit, and then you're going to just find some carbon atoms just nesting in the vacancies there, all right? So yeah, that would be steel. And so when I think about metals, you know, the crystal structures of these metals are very important in terms of, you know, properties, strength, durability. Anyone ever watched the show, you know, this is dorky, but Forged in Fire? Yeah. Yeah, so the whole idea of Forged in Fire is these, I think it's on the History Channel. History Channel? Yeah. They take just metal from like random things, all right? And they make these alloys, all right? Folding them, melting them together, trying to get the perfect crystal structure, mixture, very uniform. And then, you know, they turn it into like whatever blade or implement that they're trying to make. But what's really important is that they're, you know, they're stretching the metal material, hammering it out, trying to get the atoms to align just right. And in order to kind of freeze all of the metal atoms together in the place that they want it, they do what's called quenching, where they take, let's just say, a sword, and they dip it in this vat of oil, cooling it down really fast. But the thing is if there's any defect in that like molten metal, all right, where the crystal structure was like all loose and jiggly, and then they quench it, right? If there's any small defect, that's going to be a defect and a weak spot for when they do the testing. I hate the testing part where, because what they do is they have this guy and he takes their swords and they like whack wood with it, but all they have are safety glasses on. That's all they have. And all I'm worried about are, well, what if there's like a small imperfection, a fracture, and they hit the knife and it like splits into two, okay? Safety goggles aren't gonna help you there, all right? If a big shard of alloy comes through your face. And so I get really anxious during those parts, but I like the crafting that they do, all right? Because the whole idea of making these swords, making these alloys is they need to get the crystal structure right. They need to get the mixture composition right before they quench it. Because once you quench it, you can't go back. That's the tough part there, all right? So, because like the interstitial, like steel, like when you think of like samurai swords, like the fancy, like Japanese steel, like it's revered over other types of steel. I don't know. So how they make it is they take like a slug of iron, they put it into a blast furnace over like red hot coals, and they bury it. Because what is coal? Carbon, yeah. And so essentially they're just waiting for the carbon atoms to go into the iron under a reducing environment. That's how they make. And there's probably some like ritual. I don't know how like embedded in chemistry it is, but you know, some ritual there. All right, so that's alloys. All right, intermetallic compounds, typically these are given as a formula. There's much more order. It's not just like, oh, 75, 25% this and that. There's much more order, and we typically can give it as a formula. So for example, an alloy, you can just like talk about it in terms of a percentage of atom replacement, but intermetallic is much, much more ordered than an alloy. Okay, so those are types of metals. Rarely do we work with elemental metals, but alloys, that's the future. Trying to make better alloys, adding, you know, different ingredients to improve strength, durability, make it cheaper, you know, all of those things. That's where the future's at. So, okay. So, metals. So let's talk about what holds metals together. So I mentioned metallic bonding gave us a lot of the properties we talked about earlier, conductivity, malleability. Think about metals. We have a compound made of metals. Metals, based upon chapter 7 stuff, have really low ionization energies, meaning metals become what? Very, very easily. Metals. Cations, yeah, they lose electrons very easily. So the idea here is we have a sample of silver, all right? Silver has 1 valence electron. So if we have a bunch of silver atoms, that 1 valence electron is really easy to be lost. So what happens is that each electron on each silver atom, all of these are bonded together. They're essentially like loosely bonded to all the silver atoms, because those electrons are that valence electron is so easily lost, that this electron isn't owned by just this silver nucleus. It's actually owned by all of the silver nuclei. We call this the sea of electrons model. That's what you might have learned in high school. Do you remember learning that in high school, the sea of electrons model, where all of these electrons are shared amongst the entire sample? Those are your valence electrons. So this model, the sea of electrons, explains some of our properties. It explains electrical conductivity. If these electrons are just loosely associated with each silver nuclei, if I would put an electrical bias, you can see, oh, the electrons are going to move. All right, and so those loose electrons allow for free ions for electrical conductivity. So the sea of electrons model explains that. It also explains malleability of metals, that the metal atoms can flex next to one another, all right, that they can move past one another, those nuclei, fairly easily, because you're not breaking any single metallic bond because of those delocalized electrons. And so this sea of electrons model does in fact show malleability, because like this row of nuclei can just kind of slide past another, but there are some properties of metals that aren't explained totally by the sea of electrons model, that there are some metallic bond memory within this sea of, or these metallic compounds. I was just watching, don't judge me, I don't watch TikTok things, but I watch Facebook Reels, which is, what I've heard is worse. Is it worse? All right? It's curated for me. It's awful. And I saw this one where it was like they unfurled this is why I'm bringing it up. They unfurled a paper clip, and then they put it on a hot plate, and then it curled back. And that's because of the metallic bond memory. Yes, the sea of electron model says that the nuclei can slide back from one another, but once you do it in one direction, you kind of like mess up the structure. This is a kind of too homogeneous, but the true nature of metallic bonding, there is some metallic bond memory. So what they did is they took the paper clip, they unfurled it, they made it straight, but then they put it on a hot plate and it curled back into its original position. And that's because of metallic bond memory. And that is not explained by the sea of electrons model. I thought it was cool. Did anyone else see that thing? No one else? You saw it? Yeah, okay. All right. Okay, my algorithm is just different than yours, I guess. All right. So, yes. So the whole point here, sea of electrons model talks about malleability, but not metallic bond memory, electrical conductivity, but really the true point of this slide is that this model does not predict melting point trends of metals. So that requires MO theory. So for metals, do we remember in chapter 7 the trend for melting points of metals? What has a higher melting point, lithium or potassium? Yeah, everyone says potassium. It's not, it's lithium. Yeah, it says so on the slide. Look, as N increases, we said smaller size, lower N equals stronger metallic bond equals higher melting point. Okay, I even underlined it. So smaller atoms tend to form, smaller metals tend to form higher, stronger metallic bonds. The stronger the metallic bonding, higher the melting point. All right, so the trend is as we go down the group, the atoms actually get bigger. So we saw the melting points actually decrease as we went down the group. All right, go check your chapter 7 slides. I promise you, I said the same thing. All right. So it works going down, but what this trend doesn't work going left to right. Left to right is always messed up, right? Because when we talked about size, it was Z effective. So in order to explain melting points going left to right across the periodic table, we actually need to use what's called band theory, which is just MO theory. It's a fancy word for molecular orbital theory, which you already know. So the observation here with metals, let's focus on the D block, scantium to zinc. What we actually observe is that elements, D block metals in the middle of the D block, so manganese, iron, they have the highest melting points, the ones in the middle of the D block. While the ones on the edges, so like scantium and zinc, they have lower melting points. So what explains this phenomena is, as we go left to right across the D block, metallic bonding gets stronger. But once we get halfway full, the metallic bonding starts to get weaker. That's why boiling point decreases. It's explained by band theory, which is essentially MO theory. Because do you remember this? Do you remember this? Yeah. This was our period 2 trends for diatomic molecules, right? So for fun, because this is also review, it's chapter 12, but also review. What is the bond order for diatomic boron? How do we get bond order from MO diagrams? Bonding electrons minus anti over 2. So what's the bond order for boron? 1. What's the bond order for diatomic carbon? 2. What's the bond order for diatomic nitrogen? 3. Now for the next bond order for oxygen, where are those added electrons going? Anti-bonding. So now we are weakening the bond. So what's the bond order for oxygen? 2, and fluorine 1 and 0. So what we see here is that as we go across the 2p block, the bonds get stronger and then the bonds get weaker. They get weaker towards the end because we're adding electrons to anti-bonding orbitals. It's the same dang thing for metals, but we're not talking about molecular orbitals. We're talking about bands instead, that we have our valence band. These are our bonding orbitals. And up here, once we're halfway through the D block, we start filling anti-bonding orbitals. We call this the conduction band instead. So yeah, halfway, we start filling these electrons. We strengthen bonding molecular orbitals. But once we get halfway through, we start filling anti-bonding. All right, so it's not a new concept. It's not a new concept. We call this band theory because in MO theory, it was just molecules, so discrete molecules, like 2 atoms combine their wave function to give 2 molecular orbitals. But in a metal, are there only 2 atoms coming together? No, it's an infinite number of atoms. So instead of just 2 discrete MOs, you essentially get an infinite. So it like smears out to a band, right? And again, if you pursue material sciences or whatever, any engineers here? Engineers, materials people? No, yeah? Okay, yeah. So lots of chemistry there, all right. All right, yeah, so if you associate this trend with bond order from MO theory, then you don't have to learn something new. And I'm all about that. Okay. All right. So So we're done with metals. Metals have the most atom packing, most atom interactions. Here you can see like aluminum has 12 nearest neighbors. That each, if you looked at one aluminum atom, you could count 12 other aluminum atoms interacting with it. And so as we go from group 3, 4, 5, 6, 7, what we see is that the number of bonds per atom to complete the octet decreases. So we see some different things. As we get to the more non-metallic side of the periodic table, instead of metallic bonds, we have covalent bonds. But the difference, and I mentioned this before, is some substances produce molecules. These substances, group 5 through 7, these produce molecular solids, right? Because you can think of a molecular solid, it's a bunch of like these molecules all stacked together where IMFs are holding it together, versus something like silicon is a network covalent solid, where all covalent bonds are holding it together. There's no IMFs. So this happens as we're going left to right across the periodic table. The number of bonds to each atom to complete an octet decreases, where chlorine only needs one bond to complete its octet, so it's most likely going to bond to just one other chlorine atom, versus silicon needs 4 bonds to complete its octet, so it's going to bond to 4 other silicon atoms, which will also bond to 4 other silicon atoms, making a network. So we're done with metallic stuff, so we're going to go on to molecular solids, so like the complete opposite here. Okay, complete opposite. Yes, molecular solids. Because we already know all this stuff from chapter 11. Molecules typically have intermolecular forces associated with them. We talked about this with liquids, but it's the same thing for solids as well. When we have things in the solid phase, those weak intermolecular forces is what holds those molecules into place, so there's no translational motion. So what's locking it into place within not allowing for translational motion, we call those van der Waals forces. So you can see that in this picture, it's these dotted lines, all right? If we melt solid H2O or ice, all we break are the weak intermolecular forces, so hydrogen bonding, these van der Waals attractions between the molecules themselves. Do we break this bond? Do we break that bond when we melt something, when we melt ice, that one right there? No, we don't. That bond is a covalent bond. It's an oxygen-hydrogen bond. That's what makes the molecule. We do not break those. So same trends here. As your intermolecular forces of your sample increases, we typically see an increase of melting point temperature, just like we saw for boiling point as well. So yeah, what interaction is broken? It's all the dotted lines there. All right. And so here's some examples of molecular solids. Again, you're looking for all nonmetals, but they have to be forming a discrete molecule. So here's acetonitrile, has a really low melting point because it's a fairly light compound. It's a liquid at room temperature. And sucrose, or like table sugar, there's its formula. It's all nonmetals molecule there. It has a higher melting point, but still low enough that like you could melt sucrose to make caramel on your stove if you wanted to. All right. So yeah, when we melt a solid, we're just breaking IMFs, not the strong covalent bonds. All right. So another example of molecular solids is something like graphite. Graphite is an allotrope of carbon. There's different forms of carbon. We have diamond, which we'll talk about in the next slide. Graphite's another one. So the interactions of graphite, here's the crystal structure. We have covalent bonds between these carbon atoms. We have these sheets of carbon atoms making these hexagonal layers, all right? So graphite, I haven't used one of these in years, but like a pencil with like lead in it, right? That lead inside your pencil, because I use an iPad for everything now. I don't use pencils. It's called lead, but it doesn't contain like elemental lead. It actually contains graphite, or this structure of allotrope of carbon. So how it works, when you use a pencil and you put it on paper and you draw a line, it deposits a black line. Because if you look at the crystal structure of graphite, each of these sheets are that black line that you're drawing, but when you rub that pencil across the piece of paper, are you breaking these covalent bonds? No, you are breaking the very weak intermolecular forces between those sheets. And so that's why, graphite, when it's so easy to, it's like fairly soft, again, because it's a molecular solid, to draw those lines and deposit those carbon sheets. Yes, and then where's your IMF? It's the dotted lines between it. All right, so graphite would be an example of a molecular solid because of the IMFs between those sheets. So the other allotrope of carbon we'll talk about is diamond. There are no IMFs holding diamond together. And that's good because we want diamond to last forever. And that's where we get to covalent network solids. Okay, good. I'll get to talk about diamonds. All right, covalent network solids. Yes, they're made of all nonmetals. They often get confused with molecular, but the big difference is that There are no IMFs holding it together. It's all covalent bonds. Tons of atoms just holding on to one another really, really tightly because covalent bonds are much stronger than IMFs. So what we want to look for are like group 4A elements, so like carbon, silicon, covalent network solids, also silicon dioxide. Does anyone know the street name for that? It's glass. It's glass. The common name, whatever. All right, so because of the bonding nature of covalent network solids, all really strong covalent bonds, we're gonna see really high melting points. They're gonna be completely insoluble in water, all right? Or quartz, diamond, really high melting points, and yeah, the trends here, they're usually semiconducting or insulating, depending on, you know, how non-metallic it is. So you see diamond has a really high melting points, silicon dioxide a little bit lower, but still very, very high, especially compared to our sucrose example instead. So if you look at this picture, see, there's tons of bonds to each carbon atom. Actually, there's only 4, but each carbon atom has 4 bonds to other carbon atoms. But do you see any dotted line IMFs in this picture? No, it's all covalent bonds. So in order to melt diamond, you would need to break all 4 of those really strong bonds to carbon, and that's just not going to happen. It's just a really, really high temperature it takes to do that. So those are covalent network solids, super strong. Okay, last up is ionic solids. Okay, covalent network and ionic solids, they get mixed up too, just because they're both hard materials, high melting points, but the big difference is in the composition. Covalent network solids, all nonmetals. Ionic solids, on the other hand, are going to be what? A metal and a nonmetal. So properties might be a little bit similar, but composition very different. So high melting points, ionic solids are insulators unless dissolved or molten. And so ionic compounds, like when we think of like NaCl, salt, we know salt to be really soluble in water, but not all ionic solids are soluble in water. We know this from our solubility tables, right? That there's different solubilities of salts. But some of our gemstones that we know and love are actually ionic solids, and we know that they don't dissolve in water. So not all ionic compounds dissolve in water. And the examples here would be our gemstones, like aluminum dioxide doesn't dissolve in water. But if your ionic solid does dissolve in water, if it does, even just a tiny bit, it'll be a strong electrolyte, just like we talked about in chapter 4, and that can be one of your deciding factors there. So an example of an ionic solid is aluminum dioxide, so corundum, which is kind of the base structure of a lot of different gemstones that we know and love. So aluminum dioxide, aluminum, a metal, oxygen, a nonmetal. So that's how you identify it as ionic. Its electrostatic attractions are holding it together. So I said a lot of gemstones come from this mineral. Ruby is actually aluminum dioxide with a little contamination of chromium. Blue sapphire is also corundum, and it's just contaminated with a little bit of iron and titanium. There's also other colors of sapphire as well, and again, just different contaminants to make those different colors, all right? And so what you see here is like the different colors, the contaminations are all metals, right? It's oftentimes metals, transition metals are what give things colors, and me with my, you know, simple monkey brain, I like colors, I like shiny things, all right? So that's why I'm gonna talk about diamonds. All right, and why I personally don't buy diamonds anymore. So if the De Beers company, they will cancel me. But I want to show you in terms of science, chemistry, how I've come to this decision, all right? Also ethical in nature, why I don't buy diamonds, but so I just want to show you this. All right, so we're going to compare 3 different, so we're going to compare diamond and 2 other diamond alternatives. Diamond is just carbon. This is a network covalent compound, right? Because it's all carbons. What about cubic zirconia? So there's the formula. What kind of solid is that based upon its formula? Ionic, yeah. Zirconium is 40. It's a transition metal. Oxygen is a nonmetal. So metal, nonmetal, ionic. Very good. Okay. So moissanite is silicon carbide. So half of the atoms are silicon, half of the atoms are carbon. So if you look at like diamond, right, it's all carbon. Where is silicon relative to carbon? It's just right under it, right? So you're just replacing half of the carbon atoms with its big brother, silicon, right? So still in group 4, moissanite, which is a diamond alternative, is also a network covalent compound because silicon is just replacing it. Still group 4 elements, all right? And so what we see here, diamond, high melting point, yeah. And it's the hardest on the Mohs scale. It's 10, that's like the definition of the Mohs scales. Diamond is 10. But moissanite's up there too, 9.2. Cubic zirconia is 8.5, and fairly high melting point. So me personally, if I was just going with composition, okay, moissanite, I'm a moissanite girl. Okay, so when I picked my, my wedding ring, I chose moissanite. I just put it in my husband's cart to buy for me. Because you can do that when, yeah, you can do that. I didn't want to be disappointed, so I just bought what I wanted. So I picked moissanite, and the reasoning is because it's closest in composition to diamond. Network covalent, both of them are network covalent. I'm cheap, right? And so moissanite's cheaper, but I'm not so cheap that I'm gonna get cubic zirconia. Okay, because the cubic zirconia is so cheap, it's ionic, different composition, but it's so cheap that, you know, when we think about, you know, our rings and our settings and stuff, if the gemstone's so cheap, then so will the setting, right? Like they're not gonna put a really nice gold setting on that gemstone. So I wanna go middle of the road. Right, so that's just me personally. So that's composition. We determined, you know, the bonding structure based upon the composition. Let's look at the structure too for funsies. So there's diamond. It adopts a cubic unit cell. What's the hybridization of that carbon atom? Yeah, so let's go through the steps. How do we get hybridization? First, do we count electron domains? So we're just counting bonds. So that carbon atom has how many bonds? 4, so this is sp3. Cool. So that's diamond, it's cubic. Here's moissanite, it adopts some hexagonal thing. So let's get the hybridization of the gray atom. Look at this one. It's the easiest one. What's its hybridization? sp3. Okay, let's look at cubic zirconia. So what's the hybridization of this red atom? sp3. So structurally, all of them are similar. All of them are similar. So in the end, it's up to you what you want to pick. So can you tell the difference? I mean, structurally, they're all sp3. Can you tell the difference, which is which? They're all there. Which one do you think diamond is? What do we think? Why the middle one? It's clearest, the middle one? They're in alphabetical order. So it's cubic zirconia, diamond, moissanite. What? Yes. Yes. So that's why I buy moissanite. But these are decisions left to you and your partner of your choice. So that's just what I wanted to do. And I'm cheap. And so is my husband. So it works out. Okay. Cool. All right. We have 2 minutes. So I wanted to actually talk about my ring. Is alexandrite. And this is an interesting gemstone because I am an interesting person. It changes colors depending on what kind of lighting it's in because it has 2 absorption bands, all right? They call it emerald by day, ruby by night. So depending on the composition of light that's incoming, it'll be different colors. Like what's reflected is different colors. Yes, I was a mood ring girl when I was in grade school. And so it's reflected in this. So I wanted to show this because it's another example of, you know, cool colors, gemstones, but also I can add some chapter 6 review. All right, so here's the absorption spectrum of alexandrite. It has 2 absorption bands I mentioned. So depending on the incoming light, it could either reflect a lot of blue and red to make kind of like a purpley color, or it can reflect a lot of red if there's not a lot of blue and it'll look more like a ruby. So here are the absorption bands, all right? Those absorption bands are when an electron on its electronic structure on that atom, does it go up or does it go down? when light is absorbed? Up, yes. So if these are the two absorption bands, A and B, which electronic transitions corresponds to those absorption bands? 1, 2, 3, or 4. So you can assign A and B to two different transitions. Which two can we eliminate right away? Which ones? 2 and 4. Yeah, those ones are emission. Those would be fluorescence. So 1 and 3 will be related to absorption. So how are 1 and 3 different? They're energies, all right? So the trend is as energy increases, wavelength decreases, and frequency increases. So A is which transition, 1 or 3? 1, yes, because 1 is higher energy, A is a shorter wavelength, and then 3 would be B. Oh wait, A. Yeah, there we go. You got it, okay? So yeah, that's just me talking about myself and ranting about diamonds. So we'll finish this on Wednesday. There's only a couple more slides left, and then we'll just do final exam review.